Let's look at the next one where it says how much energy. So again, we're going to find Q. So let's see, we've got to know a mass, a C, and a delta T. It says we have a cup of coffee, 250 milliliters. So we know that the density of water is 1, right? So density is equal to mass divided by volume. And we know that the density of water is 1. If we don't know the mass, but we know that we have a volume of 250 milliliters, we know that if we cross multiply, 250 times 1 is equal to mass. So if I've got 250 milliliters, I have 250 grams of water. And then it also says we went from 20.5 degrees Celsius, so my initial temp, 20.5, my final temperature was 95.6, and it said to assume specific heat capacity of coffee was the same as the water, so 4.184 joules per grams degrees Celsius. All right, so let's plug in M times C times delta T. 250 grams times 4.184 joules per gram degrees Celsius times, we need to find the change in temperature, final minus initial. So I'm going to do 95.6 minus 20.5. We get 75.1 for my delta T. Okay, now we just need to plug it in. So we get 250 times 4.184 times 75.1. 78,554.6 joules. Wow, 78,000. So we also could put that into kilojoules. We could just say 78.6 kilojoules. Either one works. All right, and let's look at number 3, where, so you did an experiment which you found that 59.8 joules, so we're given Q, which is 59.8, was required to raise the temperature of 25 grams, so we're given mass, 25.0 grams, and it says by 1 Kelvin. So our change in temperature was 1 Kelvin. Calculate the specific heat. So we need to find, this time we need to find C. So let's plug in our Q equals M times C times delta T. You can do one of two things. If you want to say, hey, how do I solve for C? Then we're going to divide both sides by whatever mass times delta T was. So we can do that, and we can say C is equal to Q divided by M times delta T. Let's do that. We've got Q is our 59.8. Our mass was 25.0 grams. Change in temperature was 1 Kelvin. So let's do 59.8 divided by, make sure you put in parentheses, 25 times 1. And we get a specific heat of 2.392 joules per gram Kelvin. Okay, hopefully you get those same answers. Let's look at this system and surroundings here. So we're going to make some assumptions. We're going to define the metal and the water as the system. The beaker and the environment are the surroundings. We're going to assume that energy as heat is transferred only within the system. Okay, this is not perfect, but it's good enough. So the water and the metal are going to end up at the same temperature. I have hot metal at 99.8 degrees. I have water that's at 21 degrees. When we put the metal into the water, it tells us that the final temperature of the water and the metal are both 23.1 degrees Celsius. We're also going to assume that energy is transferred only as heat within the system. All right, so the energy transferred as heat from the metal to the water. So our metal to the water, so Q, the heat of the metal, has a negative value because the temperature of the metal has decreased, right? If we think I went from an initial temperature of 99 to a final of 23. So if I did 23 minus 99, right, that's our delta T, our final minus initial. I'm going to have a negative temperature. So my Q is negative. Conversely, the Q of the water is positive, right? Because if I did final 23.1 minus initial of 21, I'm going to have a positive value because its temperature is increasing. Now, the values of the Q of my metal and the Q of my water are numerically equal, but they are opposite in sign. I'm going to say that again. The values of Q for the metal and Q for the water are numerically equal, but they are opposite in sign because, do you remember, energy cannot be created or destroyed. It can be transferred. Okay, we're going to come back to this picture in just a minute. But going off of that, we know the sum of the energy changes within the system must be 0. So going off of that, coming back to here, suppose that I have my 55-gram piece of metal, say it's iron, it's heated in boiling water to 99.8 degrees, just as our picture tells us, and then it's dropped into cool water in an insulated beaker. Assume the beaker contains 225 grams of water and its initial temperature is 21. Final temperature of the metal and the water is 23. What is the specific heat of the metal? So we're given a whole lot of information here. Let's unpack. Like we just said, because of that law of conservation of energy, energy cannot be created or destroyed. We know that the Q of my water is going to be plus the Q of my metal is going to be equal to 0. Right? The total energy in the universe is not changing. So let's look at water. What do we know? And let's look at metal. What do we know? We were told that our water, we had a mass of 225 grams. We know the specific heat of water, 4.184 joules per gram degree Celsius. And we know the temperature change of water, TF and our TI. We said our final temperature of our water was 23.1 and our initial temperature of water was 21.0. So TF minus TI, 23.1 minus 21 should just be 2.1 degrees Celsius. All right, now let's look at what we know about the metal. It tells me that my metal's mass, I'm just going to put MC delta T, was 55.0 grams. We don't know the specific heat capacity of the metal, question mark. You know the final temperature also was 23.1 and that the initial temperature was 99.8. So let's do TF minus TI, 23.1 minus 99.8, negative 76.7 degrees Celsius. Okay, so we know that Q is equal to M times C times delta T. So we have all of that information. So our Q of our water, and I'm going to put this in big brackets, we're going to do 225 grams. Our mass, this is all for water, times 4.184 joules per gram degree Celsius. M times C times change in temperature was 2.1 degrees Celsius. Plus, this is for our metal, M, 55.0 grams times C times delta T was negative 76.7 degrees Celsius, and that's all equal to 0. So let's do some simplifying. Let's do all of our water, 225 times 4.184 times 2.1. So I'm going to write this down, 1976.94, and this is joules. Plus, let's simplify this. 55 times negative 76.7, negative 4218.5. We still have our C in there. It's equal to 0. All right? Let's do some more simplifying. Let's subtract this huge number and from both sides. Minus 1976.94. Okay, so that leaves me with negative 4218.5 C is equal to negative 1976.94. How do I get C by itself? Divide by negative 4218.5. Divided by negative 4218.5. So the specific heat of my metal is negative 1976.94 divided by negative 4218.5. Specific heat should be 0.469 joules per gram degree Celsius for my metal. So to go back and review, I know that my heat of my water plus the heat of my metal is equal to 0. So I just had to find out. The Q is M times C times delta T. I knew all of that for my water. For my metal, I knew M and I knew delta T. I had to find C. That was my only unknown. So I plugged in the heat of my water, M times C times delta T, simplified that. M times C times delta T for the metal. I simplified as much as I could, but I still had a C left over, and it's equal to 0. And then from there, we just did algebra to get our specific heat of our metal. Let's look at another example. Let's say we have a similar experiment where we've got 88.5 gram piece of iron. Its temperature is 78.8 degrees Celsius. It's placed in a beaker containing 244 grams of water at 18.8. When thermal equilibrium is reached, what is the final temperature? How could we go and set that up? Also, the specific heat, since we are, what is the final temperature? We do know the specific heat of iron that we just found in that last problem, but to be more specific, we could go back to the slide that had the specific heat capacities of our common materials, and we could go, oh, we have iron. The specific heat of iron is a known value, which is, let's see, let me looking back, is 0.449. 0.449 joules per gram degree Celsius for iron. And we know that water's specific heat is 4.184 joules per gram degree Celsius. So knowing these, why don't you pause this real quick and see how would I set this up? At least write down my two different columns of what do I know and where would I go from there. Okay, so let's write down our water. Let's see, we need M, we need C, and instead of delta T, I'm going to write TF and TI. We know this is our delta. And then we're going to do the same. M, C, TF, and TI. Water, 244 grams of water. Its initial temperature, 18.8 degrees Celsius. Specific heat, 4.184. Okay, iron, 88.5 grams, 449. The specific heat, and its initial temperature, 78.8 degrees Celsius. Now we're also told when thermal equilibrium is reached, that means thermal heat equal. When that final temperature will be at the same value. So let's just call this X, but it's going to be the same. X will be the same final temperature. We also know that this plus this is equal to 0. So let's plug in what we know. So we know that our 244 M times C 4.184 times that we know delta T is TF minus TI. So X minus 18.8, right? So M times C times the change in temperature plus 8.5 grams, that's our M, our C 0.449, our delta T we know is final minus initial, X minus 78.8, that's equal to 0. So let's do some simplifying. We've got 244 times 4.184, so we got 1020.896 times X minus 18.8. Can we simplify this more? Sure, we can distribute this, right? That would give me 1020.896X minus 1020 times 18.8. 896 times 18.8. 19192.8448. I'm not going to round it to the very end. Okay, this is my water. Plus, let's simplify on the right side. 88.5 times 0.449, 39.7365 times X minus 78.8. Let's distribute this so we can get rid of those parentheses. So that would give us 39.7365X minus, we gotta multiply these two together. All right, let's write this all out because we've got a whole bunch of addings and subtractings, which we know we can combine like terms here. So I've got All right. Notice that I've got some like terms. I've got X and I've got X. Let's combine those. And then I also have a number and a number. Let's combine those. I'm going to combine my X's first. Okay, that's my X's combined. Now let's combine my numbers. Minus 2, 2, 3, 2, 4, 0, 8, 1 is equal to 0. All right, let's add that to both sides. So we're going to have 2, 3, 2, 4, 0, 8, 1. Now to find X, which is our final temperature, we need to divide both sides by 1060. All right, let's do 2, 2, 3, 2, 4, 0, 8, 1 divided by 1060. 0.63225. We get a final temperature of 21.05 degrees Celsius. Now let's see if this makes sense. That was a whole lot of numbers. My initial temperature of my water was 18.8, almost 19. So does that make sense for the final temperature to be 21? Sure does, because it takes a lot of energy for water's temperature to change. So water's temperature raised, which makes sense because we had our iron with an initial temperature of 78, so it was much hotter. And iron's temperature cooled down to 21 while the water's temperature rose to 21. Good work there. And again, we just went back and we said, okay, our final temperature is our X. It's the same for both of them. We know our M, our C, and our delta T. We just plugged in TF minus TI. Same with here. We know our M, our C, and our delta T. We just did Fx minus Ti. We simplified as much as we could. We then distributed that into our X minus the initial temperature. And then we just did a whole lot of algebra and combining of like terms to find for our X, which is our TF. To finish off this first two sections, I have just some questions for you to attempt, and then I'm going to for you to pause your video. And then on the next slide, I will give the answer. So if you want to read this, pause it, try to work through it, and then I will move on to the next slide that has the answer on it. So take a minute, pause, work through this problem. All right, and hopefully you got this answer. Let's try another one. Again, why don't you pause the video, work through this multiple choice question. All right, and hopefully you got this for your answer. Let's do another one. What do we know? How do you set it up? Find the final temperature of zinc. All right, and hopefully you got the 113.2. Let's do a few more for practice. Again, read it, pause it. Hopefully you got PB. Take a minute, read it, pause it to find the mass of this copper. And it's 47.8. What's the mass of the second sample of water? Again, pause to find the initial temperature of the gold sample. And that finishes up the first section of this lecture.